Hi there, thanks for joining us on Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley, and I hope you're well. Coming up in this episode, we are going to look at, there's a whole bunch of stuff. We might not fit it all in. We'll do our very best. A meteorite versus a windscreen. Did it happen the way people think? We'll tell you. And over the weekend, there was a fireball seen over southeastern states, Victoria, New South Wales, the ACT. We'll talk about that. There's been a bit of chatter on social media, including the Space Nuts podcast group, about 3I Atlas. So we'll have an update on that. And time permitting, we will be looking at a huge black hole and a tiny galaxy. I mean, tiny as in maybe only hundreds or thousands of stars. It sounds unusual, doesn't it? And life after an asteroid impact. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And with Fred still away, we are thrilled to welcome again Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Hello, Jonti.
Good morning. How are you going?
I am well. Good to see you. Nice backdrop too, by the way. What do you got there?
So another of the pics I've been playing around with the telescope I bought about 12 months ago. This is the Pleiades. I can snap out of shot. And
very nice.
My chair immediately interferes. It's a chair captured human being, but
that was the chair nebula.
Absolutely. But yes, I get the angle of the chair just right. The AI doesn't recognize it as a human being, and we get to see it.
Yeah,
so yeah, pretty good, but I'm going to have another go at that because it doesn't quite feel right. It looks a little uncanny valley to me, so I may have to take some more photos later in the year. If the wonderful thunderstorms we're getting at the minute kind of stop, because we've had some interesting weather up here again over the last few days. There was a possible tornado within 30 kilometers of my house, which was cool. And some places got 10 centimeter diameter hail and lots of damage, and tasty stuff going on. And we might get a little bit more today and tomorrow, so it's another of those events which is spectacular and fun to watch, but you also sympathise with those who are directly in the firing line.
Yeah, we saw that. I saw those tornado forecasts pop up, and the Bureau does not often go that far with their forecasting, but they were pretty confident. So yeah, we get a few of those down our way too.
It is an interesting one. I mean, growing up in the UK, I grew up in the country, or one of the few countries that has the most tornadoes per year, which shocks everybody, but they're really, really itty-bitty-ditty ones that are associated with frontal systems. And I think a lot of Americans say, oh, no, they're not tornadoes, they're just gustnadoes or something like that.
That's right.
But in terms of the really damaging thunderstorms around the world, you've got the Great Plains in the US, and then you've got the kind of area around Bangladesh, I think. But after that, kind of southeast Queensland, northeast New South Wales is the third best place in the world for these kind of storms. And we get fewer tornadoes than the Great Plains because we get less wind shear at high altitudes. But we get equivalent amounts of mega hail, and gorilla hail is what they're calling it nowadays, which is bigger than giant hail. So we do get some really tasty and interesting stuff. And I did have one day, not long after we built this house and moved in, where the garage was still full of boxes, which is always a good thing. And this thunderstorm came in, and suddenly there's the roaring of a freight train kind of noise, which was so weird. And hailstones the size of my fist started coming down. And I had to run out with blankets and a doona to cover the windscreen of my car to prevent it getting damaged. And unfortunately, it didn't get much worse than that. But it was an interesting experience for someone who grew up in the UK, where the worst weather gets a bit of drizzle and a lot of wind.
Yeah, it can get pretty volatile in Australia, and especially in the eastern parts. Speaking of volatile, our first story is about what people thought was a meteorite hitting the windscreen of a car. And when you see the photo, it's one heck of a crack. It's come in hard, whatever it was. What is the story here?
It's a slightly weird one. There's a guy driving along. He's a vet down in South Australia, goes by the name of Melville Smith. It's his surname, Andrew Melville Smith, driving along in his Tesla, and the Tesla part is important to the story, apparently, about 40 kilometers out from a place called Port Garman, when suddenly there's a really loud smash on his windscreen. Him and his partner in the front seats get showered with glass from this shattered windscreen, and there's like an impact crater on the windscreen.
Yeah.
And obviously the car just kept on driving because it's a Tesla and they don't seem to notice when they hit things. They just carry on. All is good. Now, he thought it was weird, so he reached out to the museum in South Australia with the idea that this could have been a meteorite hitting a car. And that would be very unusual. Now, we've had occasions in the past, most famously the Peekskill meteorite, and I think it was 1994, where meteorites have hit parked cars and done a lot of damage. And I think in the case of the Peekskill meteorite, it was a fairly hefty iron or stony iron meteorite that basically wrote off the rear end of the car, and the person who owned the car was very upset until a museum bought the car for a six-figure sum, which kind of softened the blow. This case, part of the reason that they thought it was a meteorite was that there was melting of the windscreen, as well as just shattering of the windscreen. And the people at South Australia Museum basically came out with a fairly neutral statement and said, we're going to investigate this. It sounds really weird. The melting sounds odd. We're not sure what's going on. To me, as an astronomer, though, it speaks to one of the kind of really big Hollywood movie-driven myths, I think, about meteorites. There's this idea that if a meteorite falls through the atmosphere and you pick it up immediately, you'll burn your hands. It'll be super, super hot. And that just really isn't the case. Now, I mean, it would be the case if something like the dinosaur-killing asteroid hit the Earth. That'd get really hot, but you wouldn't be picking it up because you'd be vaporized and dead, right? For the smaller things that hit the Earth but can make it to the ground intact, they typically are slowed down by the atmosphere such that by the time they're 10 or 20 kilometers above the ground, they've slowed down to below the speed of sound. And so that's why when you see the fireball for these things, that fireball terminates still quite high in the atmosphere. And while it might look like it was just over the next hill from you, the thing was still 20 or 30 kilometers up. That's because the air resistance has been enough to slow them down. And at that point, they're falling at just a couple of 100 kilometers per hour at terminal velocity. Now, that's still pretty fast. And I mean, I wouldn't want to fall at 200 kilometers an hour into the ground.
No.
But it means that from a height of 20 or 30 kilometers, it takes a few minutes to reach the ground. What that means is that there's time for the rock to equilibrate, to get the temperature equalized across this entire object. Now, the object's been held in space in cold storage for millions of years. So the interior of the rock is bitterly, bitterly, bitterly cold. And they've got rocky asteroids, rocky meteorites have a fairly high thermal inertia. They're not very conductive. And so what happens is that the thin outer layer gets super hot when it's coming through the atmosphere and it's luminous. And that's getting ablated away. But very little of that heat actually is conducted to the interior. Once this thing slows down, it just keeps falling, and you've got a huge amount of cold material and a very, very tiny thin layer of hot material. So by the time it reaches the ground, meteorites are typically cold to the touch, and you're more likely to see frost forming on them or water vapor condensing on them. It's a bit like maybe deep-fried ice cream. You deep fry the ice cream, you get a hot layer on the outside, but the ice cream in the middle stays cold.
Yeah.
Same kind of idea. The one caveat to that is if you get an iron meteorite, a metal meteorite, that'll have a much higher thermal conductivity, so that can be quite warm when it reaches the ground. But rather than being super hot like the atmosphere, it's probably going to be nearer to room temperature. That's fine. What was pointed out to me, famous astronomer called Rob McNaught got in touch with me after he heard me on the radio talking about this one, because I got called out. I got called about this while I was driving back from the airport, having picked up a colleague. Talked about it, and Rob got in touch and pointed out that space junk, because it comes in at a much shallower angle, it actually ablates in the atmosphere for much, much, much longer. And it's usually much more conductive material. So you put those two things together, and if a bit of space junk were to reach the ground, there is a good chance that would be hot to the touch at the time you get to it. So another thing that you could possibly use to differentiate between whether this is a meteorite or a bit of SpaceX material. All of that put together means that the melting of the windscreen and this rock being hot, to me, actually kind of rules out it being a meteorite.
Yeah.
What adds to my argument that it's almost certainly not a meteorite is it was a nighttime event. The skies were clear in the area. Nobody saw a fireball. There are no reports of a bright fireball. Added to which, there are also no reports of sonic events or tremors, things that would show up on the seismograph. So I think we can fairly definitively rule out a meteorite as the source of this impact on this car. There is the amusing option that it could have been a SpaceX on Tesla impact, which would have been very entertaining. You know, it could have been a bit of space debris falling through the atmosphere and almost be friendly fire. But again, that would have created a very bright fireball that people would have seen. So I think we can rule that out as well. And the thing that, to me, tells the story here and will point me in a direction of investigation is in his interview, Dr. Melville Smith says, a truck went past. 5 or 10 seconds later, there was an enormous explosion. Now, I've been hit by bits of gravel falling off trucks before and had my windscreen damaged.
Yep.
Quite possible that this was a rock that fell off that truck that went past, or that the truck kicked up a bit of rock from the surface of the road that bounced along the road and hit the windscreen. I still find it hard to see how that would have generated heat from the thing that hit the windscreen that would cause a bit of melting. Even though it's been really hot there, the road surface could have been hot. You still don't expect the surface of the road to be hot enough to melt glass. But the kinetic energy of an impact, if you've got a more massive impactor coming in a bit more slowly, you still can put a lot of energy in. And it may well just be that what they're mistaking for melting is actually this deformation, this crater in the windscreen, with all of the material in the windscreen that is designed to stop your windscreen shattering. And that's done a really good job. I know when I've had cracks in my windscreen, I'm always surprised how you get a break, but it doesn't shatter, doesn't create a whole windscreen. Modern windscreens are designed to be like this multi-layer thing that stops them doing that. And I'm wondering if what they think looked as signs of melting was actually the structure of the windscreen behaving as it's expected to with a bigger impact.
Yeah.
And because this is substantial, I mean, it's bigger than some of the pictures of hail damage I saw over the weekend, for example, and it's bigger than the usual chip you see kicked up off the road. It's at a size that people might not expect it to look like that.
Yeah.
So my take on this one is, it's very confident it's not a rock from space, but it might have been a rock from truck.
Yes. Well, the timing sounds about right. And good picture of you on the ABC story on the website too, by the way.
Yeah. Back when I was younger and slimmer.
Yeah. They generally use those photos for us. It's very nice. But it reminds me of once when we had a brand new car and we decided to take it for a run, and we were approaching roadworks, and we were teaching our son to drive at the time, so he's hammering along at the maximum minimum speed of a learner. And I told him to hit the brakes because I didn't want to hit that roadwork when a truck approached, and that's exactly what happened. We got showered in gravel. That brand new car had so much, chipping on the front. We were very, very upset. To say the least. It's
shocking. I mean, one of the good things is, and it's not often that you can readily praise insurance companies, but I got a big chip on my windscreen at the turn of the year last year and got in touch with my insurance company, and they sorted a windscreen replacement free of charge without it impacting my excess or anything like that. Now, I guess it's not free of charge because I'm paying the insurance premiums.
Yeah.
But, it didn't impact my insurance rates. It didn't cause an excess. And I'm guessing that's because if you don't fix that, it can become a much bigger problem and cause them a much bigger accident. So from their point of view, it's a very valuable investment. But it does mean that when we get these kind of events, we can get our windscreens fixed fairly easily, and probably means that the trucks that are driving around shedding their loads get off a little bit scot-free compared to having people chasing them down to pay for repairs.
Yes, indeed. Okay, so probably not a meteorite, but probably a rock. Let's take a break from the show so I can tell you about our sponsor, NordVPN. With NordVPN, you can explore the web securely and privately no matter where you are, whether you're streaming space documentaries, downloading data from the International Space Station, legally of course, or just browsing from a coffee shop. NordVPN has your back. Fast connection speeds, no data logs, and protection across all your devices, including your smart TV, plus access to content from around the globe. It's like having a wormhole to the internet. Sorry about that. Without the black holes. Haha. Right now, Space Nuts listeners get an exclusive deal. nordvpn.com/spacenuts. Huge savings, plus an extra 4 months free. That is fabulous. nordvpn.com/spacenuts helps you stay protected online and gives you everyday access without any fear that your private data will be stolen. That's nordvpn.com/spacenuts. And don't forget to use the code word spacenuts at the checkout. nordvpn.com/spacenuts. facebook.com/space nuts. Now back to the show.
Roger, you're loud and clear here also.
Space Nuts.
To another event that happened over Victoria, New South Wales and the ACT, which are next door to each other, a fireball as recently as yesterday as we speak.
Yeah, so this is very much breaking news. So I'm aware this doesn't air immediately. So this was a fireball that was seen on Sunday, the 2nd of November, which as we're recording at the minute, this was actually about 18 hours ago from now, roughly. And so that means information's still coming in. It was at just about 20 to 5 in the evening, which it means it was broad daylight. So this is a daylight fireball. And to me, that's always a really exciting flag that this could be a bigger event, because to be bright enough to be seen in broad daylight, and particularly to be bright enough to be seen widely in broad daylight by the general public, means that this was a fairly substantial thing coming into the atmosphere. There are observations of this in New South Wales, in the ACT, the Australian Capital Territory, and down into Victoria. It's also a sonic boom and rumbles have been heard across Victoria, recorded on a seismograph in Nebuchen in eastern Victoria. So it kind of sounds really promising from the point of view of something that is big enough to potentially drop a meteorite. There's a lot of good footage popping up on Facebook groups like the Australian Meteor Reports Facebook group. And the one thing that gives me a little bit of caution about something making it to the ground here is that on some of those videos I've seen, this thing looks like it was a very fast-moving object. Now, typically, really fast-moving things coming into the atmosphere have a lower likelihood of leaving anything to make it to the ground. Couple of reasons for that. Firstly, they tend to detonate higher up in the atmosphere and more things get destroyed. But the other thing, which I think is more to the point, is things that come in really, really fast are typically moving on more comet-like orbits than asteroid-like orbits, and therefore are more likely to be cometary material than asteroidal material, which means they're likely to be more friable, more fragile, more dust and ice rather than rock and metal. And that means that when you see something coming in at really high speed, like some of these videos seem to show, that possibly means that there is a lower chance of something surviving to the surface. Doesn't mean that there won't be a meteorite found from this, particularly because this, like I said, was bright enough to see in broad daylight and bright enough to be quite widely observed. The fact that the explosion, the terminal detonation, the airburst, happened low enough for people to hear the sonic booms and for it to pick up on seismographs. All of these things are kind of things that we'd look for to say this is a promising event. The one thing that's giving me some caution is the very high speed. So this is very much a developing story. It might be that by the time people listen to this episode, they can go online and have a look and there'll be more information available. I'm honestly quite surprised that there's not been more media interest in this morning. Usually when there's a bright event like this, journalists are ringing up and saying, what do you think and what's happened?
Yeah.
So it may be a little bit of a slow burn, but it'll be interesting to see what develops on this in the next week or two. Maybe that nothing at all is found, but it could be yet another rock dropping to the surface of Australia to give us something to study.
Yeah, indeed. Yeah. I've never seen one myself, but we've had a few over the years crossing the sky in Dubbo. One particular daytime one that someone filmed many years ago, and quite spectacular. Okay, this is Space Nuts with Andrew Dunkley and Jonti Horner.
0G, and I feel fine.
Space Nuts.
Now, this next story takes us back to 3I Atlas, the exo comet, I suppose, that's currently moving through our solar system. The reason it's sort of gained more traction is because things have changed and it's doing weird things. And of course, that's brought out the popular press and a few of those other comments that we're not going to talk about. But a bit of chatter on Facebook through the Space Nuts podcast group. What's happening with 3I Atlas?
Well, the latest update is that it got a lot of coverage last week, not really because anything special was happening, but because last week was the point at which Comet Atlas went through perihelion.
Yeah.
So that was the time it was closest to the sun. Perihelion was on about the 30th of October. So people are obviously interested. I see the astronomer who shall not be named, they'll call him Voldemort for now, has come out with news stories saying that this thing is changing direction and the aliens are definitely invading and rocket engines have kicked off. and all this stuff. And it clearly isn't. You know, we are safe. We're not going to be invaded by aliens. You don't have to worry and protect yourself and buy some wine cocks or whatever you need to do. Does open up the question at what point this guy lost his credibility with the scientific community the best part of a decade ago. But I wonder at what point the boy who cried wolf syndrome will kick into such an extent to overwhelm the Harvard affiliation, and that the stories this guy puts out will stop getting oxygen. That's going to be an interesting study in the, I guess, the scientific literacy of journalists at the lowest common denominator publications. That might be the way I put it. But it is definitely not aliens. But what is happening with Comet 3i Atlas is it's giving us this unprecedented window into the behavior of a comet that formed around another star. It's also a comet that's coming in and traveling through the solar system at a higher speed than typical comets do, and that's, of course, how we know it's from another star. What that means, though, is that the typical process by which comets do their thing will happen in a slightly different way for this object naturally because it's coming through quicker, so things happen at an accelerated rate. And that might be what's happening that ties into a paper that's just been published that you can read on the archive, the preprint server that we as astronomers use to spread the word of our work and circumvent the exorbitant prices that journals charge for you to read them. We put all our papers on archive as well and say, don't pay the journal, read it for free here, because we're nice like that. This paper has been looking at the light curve of this comet, so how it's brightening over time. And what it's found is that 3i Atlas has been brightening faster than typical Oort cloud comets do at this distance from the sun. So when you've got a comet coming in from the sun, it brightens in a slightly predictable rate. And the reason I say slightly predictable rate is there's a famous quote from a comet astronomer called David Levy that says comets are like cats. They have tails and they do whatever the hell they want.
Yes.
And there's a truth in that. So what we tend to do is when we first find a comet, we can work out fairly quickly what orbit it's moving on around the sun to some degree, how far away it is from the sun and how quickly it's moving. And by knowing how far away it is and how bright it is when we find it, we can work out an absolute magnitude for it, which is a quantity that characterizes whether it's a big bright comet or a small faint comet. And we can use that and the orbit it's going around the sun to make a first prediction of how the comet will brighten or fade. Then, as we observe it over a little bit of time, we can characterize how its activity is changing and work out not only whether it's a big comet or a small comet, but whether it's an active comet or whether it's a very quiescent comet. So whether it's brightening rapidly or brightening slowly for a comet of that size. And over time, this allows people to predict the brightness of the comet going forward. And assuming the comet doesn't do anything unusual like fragmenting or having an outburst or something like this, we can get a fairly good handle several months ahead of time of how bright the comet's going to be with a certain degree of uncertainty. And so we've got a fairly good feeling for how a comet coming in from the Oort cloud that is about the size of Comet Atlas should brighten. Now, some comets brighten a bit quicker because they're more active, some brighten a bit slower. What's happened with Comet Atlas is it started to brighten significantly quicker than we'd expect a typical Oort cloud comet to brighten at the same distance from the sun. And that's what this paper's all about. Basically, the comet's brightening unusually quickly. Now, there's a variety of possible explanations for that, and we won't know which answer is true until we do more study. The most common reason for a comet to brighten unusually quickly is often linked to the comet's head becoming a bit more diffuse because it's a comet fragmentation event. So the comet's falling apart, you release a lot of dust as the comet falls apart, but you also increase the surface area exposed to sunlight, which means you increase the activity. And the analogy here would be the difference if you've ever had the effervescent tablets you put in water and you let them dissolve. If you get two of them and you put one in a glass of water fully intact and you crumble the other one up and drop in the crumbled one, the crumbled one reacts much quicker and it foams up really quickly.
Yep.
The solid one takes a while to go. That could be the case. We'll only know if we observe for a little bit of time, and that wouldn't necessarily be that unsurprising. There is a suspicion that this Comet 3i Atlas never actually got close enough to its parent star to be active as a comet, so it will be more equivalent to what we call the new Oort cloud comets coming through for the very first time, rather than one that's had multiple perihelion passages. And we do know that new comets have a tendency to fragment more often than older comets that have been more baked in, essentially. So that's one possible explanation, but I think another one that's really interesting and would probably fit quite well is that our models of cometary activity have built within them, although we don't normally think about it, the time at which activity driven by different ices kicks in. So as the comet gets closer to the sun and it gets hotter, different ices on the surface will reach the temperature where they can no longer be ices and they turn from ice to gas in a process called sublimation. And that's what drives the activity of the comet. And as the comet heats up, different ices turn on effectively. Now, when you're far from the sun, water ice is really cold and stays as water ice. But other volatile materials like carbon monoxide and carbon dioxide are what drive the activity of a comet when it's further from the sun. Now, as it comes in closer, it heats up and water turns on. And certainly within a few astronomical units of the sun, water is usually the dominant driving factor of cometary activity. With Comet Atlas, this brightening is happening interior to the distance where most comets would have turned on their water emission. But Comet Atlas is coming in quicker. And so therefore, it is heating up due to the radiation from the sun. But as it's coming in quicker, maybe it was closer to the sun by the time that the heat from the sun got to be enough to penetrate the surface material and start kicking on the water activity. But then that heating's happening really quickly because the distance to the sun is dropping quite fast. And so therefore you've had this spike in temperature and therefore a spike in activity. As the water activity is turned on, not so much as a trickle, but as a flood. And that ties in actually quite nicely to some of the recent stories in the last few weeks about the water vapor and the water being emitted from the comet. I saw some article about the comet emitting a jet of water like a fire hose. So this is one of those narratives that seems to fit together really, really well. Yeah. And it could just be that the high speed of the comet means that it got closer in before the water turned on, and now it's catching up for lost time. What this means for the future is that, in all honesty, we are less confident in predicting the future brightness of the comet than we normally would be. Because there's all this cometary activity going on, it's effectively having a bit of an outburst. When we were talking about it months ago, we always said it would never get brighter than about magnitude 11, magnitude 12. There's a chance it might get a little bit brighter than that now, but it's really hard to model. We don't know whether the comet will brighten further than expected, brighten really rapidly, go back to behaving as normal. It might fade away because suddenly it's had this outburst, it's clogged itself up. It might even go out relatively quickly like a bit of a snuff torch if it has fully fragmented and disintegrated. And we saw that with the great comet early this year, Comet Atlas, which was really bright and spectacular and then became the headless comet because its head just totally disintegrated and all you were left was this tail gradually drifting through space with no comet to call its own.
Yeah.
So we just don't know. There's a lot more to learn. And yeah, this is getting a lot of hyperbolic stories about it, and people arguing that it's actually the mass driver engine that's turned on as it will reroute itself to the Earth, courtesy Harvard astronomer of doom. But in reality, this is why these objects are so exciting, because they give us a window into comets with different compositions that formed around different stars, and also how comets behave at higher speed. So this is why it's cool.
Yeah, I must say I'm surprised that this one's receiving so much attention, but I shouldn't be surprised because it is a little bit different to most, and being an extra solar comet, it just makes it that much more interesting. So yeah, lots to learn really. So yeah, this one will no doubt be getting some attention for some time to come. Would be a pity if it kind of, lost itself in our solar system, but that's just the way it goes sometimes.
Absolutely.
So there it is. Yeah.
I was going to say, while we're on the topic of comets, I should just flag up to everyone, particularly the Northern Hemisphere people, but also us in the Southern Hemisphere a tiny little bit. Comet Lemon, which is getting a lot of media coverage, is at its brightest pretty much bang at the minute. It's about magnitude 4.3, which means technically it's visible to the naked eye, but in reality, because comets are diffuse objects, it'll be a very hard spot unless you're somewhere incredibly dark. But it is a very photogenic comet. It is most visible to people in the Northern Hemisphere. For those of us in Australia, it's basically lost in the glare of twilight, even though it's at a declination where it could be visible if it was in a dark sky. It's too near the sun in the sky. But these few days around now, the next week or so, is the best chance we'll get to see it from Australia while it's bright. And that'll be very low in the west after sunset as the sky gets darker. Have a look on planetarium programs like Stellarium to find the location, but my memory is that the planet Mercury is going to be visible low to the west after sunset. And if you can find Mercury and you go to the right of Mercury, it's at about the same height as Mercury on the 7th or 8th of November. So worth looking at. It is not the best comet of the year. We already have that back in January, despite what some of the articles say. But if you do want to see a comet that's borderline bright enough to see the naked eye, that's your one. It should be quite good in binoculars. And certainly for people doing astrophotography, have a look online. Some of the photos of this thing are really spectacular. There's people who've done, pretty clever things, imaging it with lovely foreground views like lakes or rocks or castles or whatever. Yes. So there's lovely images of this comet out there if you want to feast your eyes on what people who are talented photographers can do.
Yes, very good. That's 3i Atlas. Now, and you can read about that on the archive website, as Jonti mentioned.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Let's move on to this really interesting story. An enormous black hole has been found, but what's really interesting is the galaxy that it's in is tiny. And when I read into the details of this story, we're talking a galaxy with very few stars, surprisingly few stars.
And this fascinated me reading it. Now, I always say, particularly when we're doing the questions and we get lots of cosmology type questions, I'm not a cosmologist. I'm not a galactic type astronomer. My expertise and my focus is very much on the things closer to home. So I tend to try and pick stories where I can talk from a position of some authority rather than no authority, if that makes sense. But this story was so cool, I thought we had to include it, even if it might be a little bit of the blind leading the blind in a way. But this is one of the Milky Way's satellite galaxies. And our galaxy has many, many satellites, from the incredibly large and bright Large and Small Magellanic Clouds, which we can see here in the southern hemisphere, really high in the sky at the minute, really spectacular, down to really, really tiny satellite galaxies that almost push our understanding of what it means to be a galaxy. And this galaxy is one such galaxy. It's what's described as an ultra-faint dwarf galaxy. And there are likely an enormous number of these in space that we just don't find. I guess the analogy I'd use here is that if you go out and look at the stars in the night sky, the stars that you're seeing are very much the superstars of our galaxy. They're stars that are much more massive than the sun, that we're seeing from great distances. The most common stars in the galaxy are the dim little red dwarfs like Proxima Centauri. And Proxima is fairly massive and fairly luminous for a red dwarf. It is the closest star to the solar system, and it's too faint to see with the naked eye by a factor of 100 times. So there's lots and lots of very small faint things that until we had telescopes we couldn't find at all. There are always more small things than big things. So it seems likely that there are many, many, many faint, ultra-faint dwarf galaxies that have simply not been discovered, even in our local area, never mind the far parts of the cosmos. When we talk about galaxies that are many hundreds of millions of light years away, we're only seeing the superstars. We're not seeing the little baby ones like this. The galaxy in the story here is called Segway 1, and I must admit that I don't think I'd ever heard of this, or I'd only ever heard of it in passing before this story came out. It is really tiny and very anonymous. It's about 75,000 light years from the Earth. Like I say, it's one of our satellite galaxies. And our best observations, there's a photograph in the Space.com article, which is fabulous. It says, here's this dwarf galaxy with only a handful of stars, and I'm not sure where the galaxy is, because there's so little in the photograph. Yeah. That's what it's like. And so you're talking here of just a few hundred or a few thousand stars held together. Now, that's been a puzzle for galaxy astronomers for a long time, because so few stars have so little mass that the galaxy shouldn't hold itself together. The galaxy should have dispersed over time. And for a long time, the best explanation people have had for this is that these are kind of dark matter galaxies, that they've got a massive dark matter agglomerated as a big dark matter halo, giving you enough mass there that we can't see to provide enough gravity to hold this very small number of stars together, to keep them kind of whizzing around one another. And that kind of makes sense. It's, we know that a lot of galaxies have big amounts of dark matter. In fact, all galaxies do. So you could almost have dark matter galaxies where you've got a clump of dark matter with very few stars. That kind of made sense. But the news story comes from improved observations of this galaxy, coupled with some computational numerical orbital modeling. And what they've found is that the stars near the middle of Segway 1 are going round the middle really, really quickly. Now, that allows us to take a measurement of the mass that is closer to the middle of the galaxy than those stars are. So anything feels gravity from the things closer to the middle than they do, fundamentally. So what this means is by observing those stars that are in the middle of this galaxy, seeing them move, we can weigh the very innermost parts of that galaxy. And what that tells us is that there is about 450,000 times more mass in the middle of that galaxy than the mass of our sun that we cannot see.
Yeah.
Which makes this a black hole, and it makes this a supermassive black hole, albeit a relatively low mass supermassive black hole compared to the one in the middle of the Milky Way. Now, that in itself is not hugely unexpected. Pretty much all big galaxies have supermassive black holes, but we've not really seen them in teeny tiny little galaxies like this before. Even more so, we've not really seen cases where there are galaxies whose black hole is more than 10 times the mass of all of the stars we can see in that galaxy. Feels like a really kind of weird imbalance. The black hole is more massive than the galaxy around it seems to suggest there would have been enough material for. But it's really weird from a few reasons, but really cool in the same way, in that it's suggesting that this galaxy is not held together by dark matter. It's held together by this supermassive black hole at the middle. That maybe gives us an insight into how other ultra-faint dwarf galaxies behave. This is probably not alone, suggesting that there could be a lot more of these supermassive black holes out there in the cosmos than we thought. It also possibly is a bit of a hint that Segway 1 was once a more massive galaxy. You know, if you think about the idea of the mass of this supermassive black hole and think, well, what kind of galaxy would normally expect to have a massive black hole like that in its center? How many stars should it have had? Maybe Segway 1 was like that in the past, but because it's so close to the Milky Way, it has been continually stripped and denuded of its stars from the outside inwards by our galaxy essentially playing Pac-Man and gobbling it up, going nom 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 essentially, which is how galaxies grow. Galaxies grow through cannibalizing their neighbors. And we see that to an extent even with our largest satellite galaxies, which have been disrupted and devoured a bit by the Milky Way and will eventually be gone. So there's a lot in this. It is a really fascinating story, albeit one, like I say, where I'm much further from being an expert than a lot of the other stuff that we talk about. But you can find more about it online, and it is just a really cool little story. You know, it may well totally revolutionize our understanding of how the smallest galaxies work.
Yes, indeed. You kind of took the question out of my mouth, but I wasn't thinking of a neighbouring galaxy stripping the stars away from Segway. I was thinking the black hole might be devouring the stars within its own galaxy. But
well, you'd probably get a bit of that as well, because the thing with the black hole is that its gravitational pull is exactly the same as a group of objects of the same mass would have. So it doesn't really pull things in any harder than the material that was there beforehand. But if you've got a neighbouring galaxy like the Milky Way stirring up and numbing on this galaxy, it will also stir up the orbits of the stars in that galaxy, making some of them sufficiently elongated that they could fall onto that central black hole. So it's likely that the process of the Milky Way eating this galaxy has also led to the black hole in the middle of it getting a bit of a feed as well. A bit like the white dwarf we were talking about last week, getting fed asteroids by the planets going around it. Same kind of idea.
Yeah, it sounds like these stars in Segway are like a school of fish being attacked from all sides by predators, and eventually they'll just all be gone. You can read all about that at space.com, or you can look at the paper that was published in Astrophysical Journal Letters.
3, 2, 1.
Space Nuts.
I think we've got time for one more quick yarn, Jonti, and this is a story that I find fascinating and certainly relates to the history of Earth in many ways. Life after an asteroid impact. Now, a big asteroid conking the Earth can have cataclysmic effects, as we've seen in our history, and the geology certainly backs that up. But, fast forward a few gazillion years, or whatever the number is, and life does return. They've been looking into this effect, haven't they?
They have. This is some lovely research that's come out of Finland, where there's a beautiful impact crater, and I will apologise for anybody listening who speaks a beautiful Finnish language, but there's a beautiful impact crater in Finland called Lake Lapajärvi, which is an impact basin about 23 kilometers across that was formed 78 million years ago. It's a fairly hefty impact. It's the kind of thing that would be a bit of a drama if you lived in that part of the world, but not large enough to cause a global mass extinction event. So this is nothing like the one that killed the dinosaurs 65, 66 million years ago. This is a bit smaller, a bit more run-of-the-mill. Now, there's a vague, rough rule of thumb for impacts that if an impact happens, the size of the crater is about 19 times the diameter of the impactor. So that tells me that the rock that hit to create this crater was probably a bit more than a kilometer across. So it's fairly substantial. That's the kind of impact that statisticians would argue would kill about a quarter of the world's human population. So not an extinction event, but a very bad day. The team that have looked into this were really interested in how quickly life can reestablish itself in the rocks left behind from an impact. Because you have an impact happen, it superheats and sterilises the rocks. This would have sterilise the rocks in the impact site by heating them to more than 2,000 degrees C. That's 3,600 Fahrenheit for the Americans. Enough to kind of really sterilise the place it hit. It would have also, though, caused huge temperature gradients. It would have shattered the rocks, and it would have driven some interesting chemistry. So that means that once the clouds clear and there's time for things to settle down, you have a site here that is similar to the kind of conditions at locations where people think the first life on Earth may have got started. So there's some interest in what happened after. So to study that, this team have gone to the store of drill cores that they can get to in Finland, where there are resources left behind from drilling expeditions that dug into this crater lake back in the 1980s, 1990s. Mm-hmm. And this is a really good example, incidentally, of how legacy materials continue to have worth. And we've talked about that with the rocks from the Apollo missions, where they put a lot of them and preserve them for future use, because our technology improves all the time. So we can go back and look at things that were collected in the past and get new insights. So the team went back to these rocks that were dug up back in the 80s and 90s from drill cores that dug down all the way into this crater lake, into the floor of it. And they got 33 different drill core samples from different locations, looked at them essentially with a microscope and a pair of tweezers, and plucked out a number of crystals of calcite and what was the other rock? There were a couple of things, calcite and pyrite, these rocks. Yeah. And they used these for chemical analyses. And what they were interested in doing was getting a chronology of what happened in the years after this crater was formed. Now, similar work has been done before for the Reese crater in Germany and the Horton crater in Canada, which suggested for those craters, the material under and around the crater cooled fairly quickly in geological times. For those craters, it cooled to about 50 degrees C within 250,000 years for the Reese crater, and for the Horton crater in Canada for about 50,000 years. So that cooled down fairly quickly. But this Finnish team, looking at these crystals from this beautiful Lake Lapiavi, found that it took about 4 million years for the rocks to cool to 50 degrees C, which to me is astonishingly long time. That's very slow cooling.
Yes.
And they're saying we don't really understand why it took so long, but it's probably to do with the kind of rocks that were around and the kind of insulating properties. But what they did then was that they looked at the chemistry of these samples. They used mass spectrometry to look at basically the different isotopes of oxygen, carbon, and sulfur in the rock. And they were doing that because microbes tend to process oxygen, carbon, and sulfur and preferentially use one isotope over the other, so they can put this very distinctive chemical signature in to what's left behind. So the team were very much looking for, in addition to this cooling data, the point at which you started to get the fingerprints of microbial life once again. And what they found was that 4 million year point, when it cooled to about 50 degrees C, that was when you started to get life there again. And you started to get life that was turning sulfates into sulfides. I think that was the chemical terminology there. So they were processing materials and life had recolonized effectively. Yeah, sulfate into sulfide. That was after 4 million years. 10 million years after that, the temperature dropped to about 30 degrees C, and you got the kind of microbes that make methane recolonize there. So you've now got this really nice chronological timeline of the recolonization of this site. And they talk about this being a surprisingly quick time. To me, this is surprisingly slow, given how much life we've got around on the Earth. So Obviously, they are more expert than I am, and I'm happy to take their word that this is a very quick recolonization. But to me, it's interesting that it took it so long to cool down and for life to get going again afterwards. That's maybe telling us something about the kind of rocks the impact happened in. I don't know whether it could also be telling us something about the underlying geology of the area at the time. I'm just not expert enough. But it's a really fascinating study, and it's a really good example of how the science of astrobiology, which is the science of the search for life elsewhere, and the science of the question of are we alone in the universe, and of how did life get started on Earth, all those really thorny questions, that's not a science that can be answered by just one discipline within astronomy. It's a really multidisciplinary area where you need people from an incredibly wide and diverse variety of areas in the sciences to come together, because no one area has the knowledge and the skill set and the methodology and the samples to provide an answer on their own. It's why conferences on this kind of topic are so fascinating to me, because you go to talks from biology and chemistry and geophysics rather than just a lot of talks from astronomers on astronomy things. And this is a kind of study no one I work with directly would have been able to do, but these people have been able to drill down, do this awesome work, and get some really fascinating results. So I'm looking forward to hearing more about this, and to be honest, this would almost set the scene for groups elsewhere in the world to start drilling down into other craters to see if we can get a feel for, is this unusual? Is this common? And the other two unusual? Essentially what's going on.
Yeah. And as you said, it's just great that historical studies are being dredged back up and reused with modern techniques and technology to find out more. I think that's amazing. And keeping rocks for future reference when we can do things even better may reveal more answers. So that in itself is a terrific part of that particular story. And I was just wondering about the Tim Horton, the Horton crater. It couldn't be named after Tim Horton, the famous ice hockey player, could it?
Ice hockey player? Are there not some famous pancakes? Kind of Tim Hortons.
Yeah, well, that's I mean, you can't go to Canada and not go to Tim Hortons.
I think the spelling may be different. This is Horton, H-A-U-G-H.
Right.
So probably a distant relative.
You never know. Okay, that brings us to the end. Jonti, thank you so much.
That's an absolute pleasure. Thank you.
Good to see you. Jonti Horner, Professor of Astrophysics at the University of Southern Queensland, joining us. Don't forget to visit us online at our website and check everything out. You can send us questions via the website as well, and check out the shop, and maybe sign up to become a supporter. Whatever floats your boat, it's at spacenutspodcast.com. And thanks to Hugh in the studio, who couldn't be with us today. I don't know if you know this about Hugh, but he's a bit old school. He doesn't use sat-nav, but he heard about this great new book, and he's gone to a bookshop to try and get it today. It's the 3i Atlas book. I'm not going to tell him. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.